Okay, so I wanted to kind of go over the week 3 reflection. We got a lot of good answers in your in our discussion for the representation of a line. So I gave you guys this line right here, right? This vector equation for a line in space. All right, and I asked you for two different representations. Now, a lot of you gave me the parametric and the symmetric. Some of you rewrote it like this, which I don't consider different, right? But it still represents the line, right? Now, one thing that I want to make sure that we're clear is that in order to represent a line, right, we need, so representing a line in space, when we are in two dimensions in our x and y plane, we needed really a point and a slope, or 2 points, and then we can find the slope from there, right? In 3D, so 2D, really what's required, either 2 points, remember how to spell here, so 2 points, or we can get by with a point plus a slope. All right. Now in our three-dimensional space, which we're dealing with in this course, right, what we need is a point on the line and a direction vector. All right. So we need a starting point, and then from there, in what direction should the line head, right? And usually, unless stated otherwise, we'll assume that the parameter t that we use here is all real numbers, unless we need it to be. If it isn't, then it doesn't it represents a line segment and not so much a line, right? When we say a line, we're assuming that a line goes off in both positive and negative infinity, right? In those directions. Okay, so if we're given this and we say, all right, find two separate representations, one easy thing we can do is, well, let's change that. I can change the direction vector, right? Now, what I mean by change is not the direction itself, but the representation of this vector, right? So if we look at our equation here, the direction vector that for this given line is 3, 1, 1. Right? So any vector proportional to that vector will work, right? So let's say I'm going to multiply it by -3 if I wanted to, right? So all right. Okay, so that direction vector, while it's not the same, it is proportional, right, by a constant factor of a -3 that I multiply. So I can have my new line to be 3, 0, 3 with new direction vector 9, 3, 3. All right, and that is a different representation of that vector equation that I have above. Okay, so another thing I can do is, remember 3, 0, 3 also represents that point is actually on the line. Right? I can change that, right? I just need to find another point, right? So here, let me change the constant part. Find another point on the line. All right, and what I can do there is, let's take our original equation and let's just plug in, let's say, how about -1? All right, again, I just chose that, right? It's a parameter. I can choose any value for t, right? Since it is defined from -infinity to +infinity. All right, and doing that, we get 0, -1, 2. Okay. Now, again, this is a vector starting from the origin, and it has its tip at the point 0, -1, 2. it's also a point on the line. Right, so for my other representation, and let's see, maybe I should rename these, right? Instead of R, let's call it A of T. All right, just so we are differentiating between both of these, right? And then my second representation could be, all right, I'm going to use that as my constant, -1, 2. Okay, and I'll keep the same direction vector that I had to begin with. Right, and there we have a second representation of it, in this case where I change the constant part of my vector equation. All right, now these are not unique, my A and my B, right? We can come up with essentially infinite amount of representations for the exact same line, right, in our vector form. All right, so thank you.